Hello, and thank you for joining me. Today we're going to discuss XGBoost, which is a pretty famous model, and you probably have heard of it. We're going to look at a fairly famous data set, a concrete compression strength test, and we'll have some fun with this classic data set today. Okay, so XGBoost is one of the few models that's really commonly used that's not from Sklearn. Sklearn has a great set. It has a version of XGBoost called gradient boosting, and we'll compare those two next to each other today to really see the difference and see if we can get kind of more of the standard library to work as well as this famous XGBoost machine learning model, because they use essentially the same type of mathematics. XGBoost is really classified by having a lot more flexibility and detailed control over lots of the parameters. But we'll play around with all of those today as we go through this class. Okay, so importing data science libraries or standard data science libraries, gradient boosting from and regressor from the ensemble method or sklearn.ensemble, XGBoost and XGB regressor, standardization, and a few other data science libraries, train test split, and then turning off some warnings here. Okay. So importing the concrete compression data set. And typically, again, you normally do the SCS MPA score. We're going to predict a water in this one, just having a little bit of fun, something a little bit different. There's no reason you can't. Okay. So going through this and iterating through the distributions, I noticed that there's this interesting distribution here where there's a lot of values at 0, and this happened for a few of the columns. What I ended up doing, I note this now, and I wanted to, it's good to explore your data all the time. And this is, if we pay attention to what this is 0, anything times a 0 is a 0, right? So this value specifically could be an event more than it's a 0. It could be just it's non-existent, and that might have something to do with, in this case, our water level in our concrete. And so I thought maybe if this is an event, we should one-hot encode these features for when it's 0. We're going to one-hot encode a feature that says a 1 so that our model has a way to essentially just push it off. We just give it a 1. Anything but a 0 it can use, and it will find the best way possible. Okay, so this is kind of the only thing to really note about the distributions. Lots of kind of funky distributions, but not doing a ton of pre-processing because it's not really the point of today's class. So the no null values to deal with, a little bit of a weird exponential distribution here. So I bucketized this one to deal with the effective distributions. Just using pd.cut, gonna cut the age one into 4 different bins and then just classifying the bins like this, the outside edges, and then the labels the bins will be in, just super simple A, B, C, D, just in case I decide to kind of move these around. Okay. One-hot encoding those with pd.getDummies. I'm going to, when slag is equal to 0, this would by itself produce a true and false Boolean output. If I multiply that by 1, changes nothing. 1 times 1 is 1 times true is 1 because trues are equal to 1. 1 times 0, 1 times false is equal to 0. So it doesn't change any values, but it changes from true and false to 1 and 0. Okay. So doing that for slag, fly ash 0, and creating a new column, fly ash 0, and then super plasticizer 0. Okay, so doing that for 3 columns, and then train test split, and going through these, putting all our one-hot coded, our new one-hot encoded features for signifying when it's 0, the one-hot encoded age category, and then our other features predicting our water content in our concrete. Okay, train test split, pretty standard. Standardize, PCA. PCAs don't always work. I always say PCAs are a good experiment to do, and if I wanted to turn this off from my workflow, I could just comment this out, restart run all, and see how well my model does with or without. Standardization always works. PCA is something that it usually works about 90% of the time, I would say. So it's something that's a good experiment to set up. It's not a default. It absolutely will work out though. So it's a kind of an experiment that you should do though, because you just get an extra, few points on your score at least. Sometimes 5 or 6 extra points. Really doing it nothing extra. Okay, so here just going side by side, looking at the gradient boosting regressor from Sklearn and the XGBoost regressor from XGBoost. Okay, and so you can see out of the gate, the XGBoost works a little bit better using the default parameters, not significantly better than XG or gradient boosting regressor, and they use the same mathematics, so they realistically shouldn't be all that different, less than one whole r squared point, 1 percentage point less. So we'll go and try this out. We'll see a few things that are specifically different. One of the, and I believe I put this in the class, but or in the post that I did for this, but we'll find that there are just a lot of extra things that we can control that you really need to have a lot of time to be able to do that, but you'll also be able to find that it'll probably work more tailored in certain data sets where you're able to find the massive amount of hyperparameters that you're able to use. You can fine tune those in a certain way. Gradient boosting regressor has, in Sklearn, has all of the major ones that I feel like you really need, and you can get it working quite well and really very comparable to the XGBoost, if not just as good. Very marginally, sometimes a little bit less, like you can see here, but if we have studied hacker statistics at all, we would know that we cannot statistically prove when they're so close like this that one is really better than the other. This could just be the random split that we chose, and if we did a different random split instead of 42, try a different number, you might find that the gradient boosting regressor from Sklearn works better. Okay, so basically very comparable. They all are both showing some signs of overfitting, although the gradient boosting regressor is showing a little bit less overfitting. So tuning the estimators. So I ran through a loop of 5 to 500, going up by 5. So really all of the, as many as I could plot for this. Building a couple list train test scores for gradient boosting and XGBoost, extreme gradient boosting. Fit the gradient boosting with the different estimator, get the scores, append the scores, do the same thing for XG regressor, XGB regressor, different estimators, get the scores and put them in here. I then plot a line plot for each one of these for the train and test scores. And the test scores are the darker versions, and the test score blue is the gradient boosting, red is the XGBoost. So red is kind of the one that we'll focus on today and really make comparisons with the blue, the regular gradient boosting model. I then select taking the estimator, the list of estimators that I did. I take the argmax of the test scores, and this gives me the position that this, gave me the best score of this. So by finding that position here, I'm able to pull that best position out of the n estimators and then say, oh, easily put this in the plot so we can see 480 was the best gradient boosting, and XGBoost 140 was the best one here. Although you can see very minor difference after a certain point in the actual boosters. Gradient boosting did need quite a few more to become substantial, but you see that gradient boosting here worked quite well quite quickly. Okay. Max depth. So we can see here, now we have our best estimators trying max depth now. So the same whole loop, but looking at max depths from 2 to 20, well, that would be 2 to 19, everything inclusive and then exclusive, Python indexing. And you can see here that train test, it really tends to do quite a bit worse on our test score for the gradient boosting after a certain point. The regularization factors in XGBoost helped us perform better even with larger, deeper trees, which normally would prevent, as you can see with the regular gradient boosting, create a lot of overfitting happening, and it's not seeming to happen as strongly with the XGBoost, although the best scores are still at the 5 and 4 right here. Smaller trees, maybe not by themselves, but in an ensemble method, kind of simpler, stupider trees tend to work better in an ensemble method. So we really want the most advanced models in an ensemble method to work well. Max features. Okay, trying max features going from 10% all the way up to 100%, going up by 1% intervals. Trying those again in max features, so the percentage of max features I'm going to use. XGBoost, it didn't really make a difference at all. Really, it has pretty stable throughout this. We can see that as we trained the gradient boosting, it did really make a large difference in how well this was fitting though. Okay. And Bootstrap, this was not Bootstrap, this is subsample. I'm gonna change that right now, I made a spelling mistake. I tried to do Bootstrap, but gradient boosting doesn't have Bootstrap available. So looking at subsamples, so this is the percentage that we're using at every split, how many subsamples, what percentage of the data we're going to use in determining that split on each node. Okay, and so going through this, and we can see that test score did quite well, almost as good as the gradient boosting. It seems we're still a little bit better. We're beating it a little bit there, but you can see basically they're very comparable all the way through. Gradient boosting needed to get a little bit higher to start working as well, and it really started working well when we have a larger, basically using all of the features, is when it tended to beat the gradient boosting as well. Unlike gradient boosting that did well, we're only using 40% of the features was its best score, although there was times that it came very, very close to that as well. That's one thing we have to be careful when we're tuning the hyperparameters, is that even when you do this automatically on a grid search, if you look at the grid search, you'll be very surprised that your best model is only very, very marginally better than the next maybe 10 or 15 models in those parameters. So you really have to look at the grid search really and see how many, really what your model is actually finding to be the best one on average or overall. Because really, if it finds that, really generally bigger estimators are better, it might not be that on this specific train test split it found to be good. It really might be just that bigger ones work better out in the real world. So we just have to be careful that small differences do not really hold up in real life because they're not statistically different. We can statistically prove that one is better than the other. It could just be because of the random sample. And random samples have a little bit of randomness baked in terms of we randomly selected these people, but we're going to be using our model out in the real world on the population. So we need to understand that these little differences are almost meaningless because we did not get these from testing it on the whole entire population. Okay, we can see that we are able to get the XGBoost working better here a little bit in this situation. Okay, learning rate, because this is using gradient descent, learning rate is very important, although we don't need to turn this down anywhere near as low as you would a typical deep learning model. I usually find 0.1 is the best one, so I kind of tuned a lot of learning rates around that and just try and see what works the best. And we can really see that they all really worked well, but we can see that the 0.08 worked well and 0.012 worked the best here. Okay. And so really truly, it just, as you had a bigger learning rate, it did not necessarily work well for the gradient boosting. We needed something to actually be quite a bit, and it's kind of hard to see in this map right here, but really we needed a very small learning rate, and you can actually see very slightly see that the XGBoost is doing a little bit better in this area right here, and it just kind of drops off the cliff as we start to get into relatively high models here. And so gradient boosting is acting a little bit more sensitive, like we would expect a neural network to work, in the sense that we need a very small fraction of the errors being passed to the network. And here we need a very small amount of errors to be predicted in the next tree. Okay. And so booster type. So this is something that we only have for XGBoost. And so the next ones that we have we're only going to tune for XGBoost because they're not available in Sklearn's gradient boosting regressor or gradient boosting classifier. So we can choose the type of split or the type of decision tree that's going to be. So GB tree, GB linear tree, or Dart. Okay, Dart is the standard one that is used with gradient boosting regressor and Sklearn. Okay, so doing the same things, just doing it for one tree, and we could see that really GB linear was the only one that did not work overly well. It didn't work terribly, but the Dart one, or sorry, GB tree was the best one, but the Dart is very, very comparable in this as well. Okay. And that's kind of one of the reasons we were able to get a very good score in the gradient boosting regressor, because it is a good algorithm that makes up the decision trees in Sklearn. Min child weights, and so this is going to decide how much do we put on a child, the final branch, before we decide that we're not going to split this. Basically, how much data can we have at least needing to reach that last node before we would say there's no reason to continue to do splits. This is kind of similar to min sample split. It kind of works similar to the min sample splits in random forest. Okay. So min, just testing all of those, and really you can see here it didn't make a huge difference in any real sense. Gamma controls the loss reduction in how it's going to determine whether to do a split. So this is going to basically affect its ability to do a split, and so we're going to pass gamma from 0.1 all the way up to 1 and test all those, and you can see it does make a little bit of a difference and not a substantial factor here, and that's what I found is these XGBoost specific hyperparameters are a little bit more, are very the fine tuning. It's not going to be substantially different. Very small differences, I would say, from these. But they can be the difference in making this model work better than the standard Sklearn gradient boosting. Okay, so you can see here we got 0.1 was the best one for this one, although really saying kind of the lowest, although you can see as well 0.85-ish worked really well as well. The alpha is the parameter that's going to allow us to do regularization like L1 regularization, again trying all from 20% all the way up to 100% of regularization and using the alpha, and this is going to control the L1 regularization that's going on with this. Again, it does make a difference, not anything substantial, not anything clearly worked better than the other one here, but we can say it's 3.4 is working the best. So it is, I kept collecting these, what worked the best as I went through, and we can see here we're going to test the gradient boosting regressor and then the XGBoost regressor here. And what we can see is in the end, they are basically very common. We improved both of them. They are both basically very good. There's not this huge substantial difference in either one of these. They both work well. But here what we can see is, again, they're both really overfitting now as well. We got to kind of squeezed out the most that we could of these on the training data. But we'll see here that they're very comparable. You might be able to squeeze a little bit more out of the gradient, or sorry, the XGBoost regressor. As you can see, we did a lot of hyperparameter tuning, and it basically is still comparable, right? Just like when we started off with the defaults, we did all of that work to increase the score by 2 points, which could be valuable. Are we going to increase the XGBoost regressor 2 points higher than the gradient boost regressing? I don't know. I would say it's not super likely. The gradient boosting regressor is the one that I normally use. It does work very well, and it's truthfully one of my favorite models. The Sklearn gradient boosting works well, although the extra trees is my favorite, my second favorite of the other kind of main class type of ensemble method. Okay, so thank you very much for joining me today. Don't forget to hit the subscribe button down below, and I will see you next time.